Okay, so we're going to take a look at one of the questions from the 2014 AP Calculus AB exam. This is question 2 from that exam, and in this video we're going to look at part A. In subsequent videos we're going to look at parts B and C. So part A, question 2, says let R be the region enclosed by the graph of f at x equals x to the fourth minus 2.3x cubed plus 4, and the horizontal line y equals 4 as shown in the figure above. And we can see that they've drawn the graphs for us and they've identified the region R. Part A says find the volume of the solid generated when the region R is rotated about the horizontal line y equals negative 2. Well, if we look at this function, we can see that this is going to have a y-intercept of 4. And so we know that this height up here is 4. And so we know that when we revolve around the line y equals negative 2, that's going to be down here someplace. And so this graph is going to extend way down the page. So the first thing we need to do is we need to get the graph of this. So I've already set up part of this. And we see that the graph that we were given before with the region R shaded in here, and this region needs to be revolved around this horizontal line y equals negative 2, which is going to reflect this curve and this line down to here. So if I now start sketching my revolutions, I see that I'm going to have the first one on this edge is just going to be a big circle. On this edge, again, I'm going to have a big circle here, which is going to extend into the page, so we'll be able to see all of it, something like that. And if I take a slice out of the middle, this is the part that really matters to me. If I take the slice out of the middle, I can see I'm going to have washers here. I'm going to have a big radius coming down like that, and I'm going to have a smaller inside radius like that. The region that I'm going to be working with here, the slice, the washer if you will, is going to look something like this. And as is always true, if I can get a good diagram, if I can do a good job with the diagram, I've got a pretty good chance of getting the rest of the problem right. So we'll take a few minutes and try and get a decent diagram. So now we can sort of see that washer. It'll be a little better when I bring this out into 3 dimensions, so I'm going to make this a little bit thicker. Give that some thickness coming down there. And I can sort of imagine this coming out of the board. Likewise, the inside part, going to need a little bit of thickness. And I can imagine this now coming out of the board at me. And now we can see our washer. All right. So now we're ready to start solving the problem. The first thing I need to know is I need to know where these two curves intersect. So I've already been told the function was labeled originally as f at x up here. So I should label my graph, but I don't need to write the whole thing out. I can just come in here and say this is going to be y equals f at x. And I need to solve where f at x equals 4 to get that point of intersection, to find out what that value is there. So I set f at x equal to 4. And I've got a calculator, so I just put that into the calculator and solve it. And the calculator comes up with x equals 0 or x equals 2.3. So I can see here that must be 2.3. Because I'm dealing with washers, I must have a big radius and a little radius, and this is kind of the trickiest part. So my big radius, I can see, is going to go from the line down to there. That's going to be my big R, and so I'm going to label that. Whoops. I'm going to label this as being capital R. And my little radius is going to extend from here down to the axis of revolution. So this is going to be my little radius. To calculate these, I have to recognize that this big radius is really made up of 2 parts. I've got this part here, which I know is 4, and this part here, which I know is 2. So the big radius is just 6, And no matter where my slice is as I move across here, that big radius is always going to be 6. So that's sort of easy, and I can just write that down now. Big R equals 6. It's a constant. Now I need to find little r. And to find little r, I'm going to look at this again. Here, I still know that that distance is always 2. And this distance, well, this distance is going to depend on the height of the curve. This is my y value, and this is f at x. And so that distance is f at x. And so I can see that my little radius is going to be this f at x plus this 2. So I've got f at x plus 2. Now I've done just about everything I need to do. So I can write down the formula for my volume. And my volume is going to equal the pi times the integral from 0 out to 2.3 of big R squared. And I know that I'm doing this with respect to x, and so these better be functions of x, minus little r squared as a function of x. And I've already figured out what those things are. This is going to now be, just move this over a little. This is going to equal pi times the integral from 0 to 2.3. My big radius I said was 6, so 6 squared is 36. My little radius I said was f at x plus 2, so this is going to be f at x plus 2. I'm going to square that with respect to x. And I now have everything I need. I can do the rest of this in my calculator. And if I go into the calculator, what I would do is first I would assign f at x to that function that I was given in the beginning. I believe is it a cubic or a quartic function? This quartic function. So I would start by defining f at x in my calculator. I would set these things equal to each other, and I would have had x equals 2.3. And the 2.3, I would have probably called that a, and used a in my calculator. And then I can just type the whole thing in. When I do that, and I've taken a screenshot of what comes on the calculator, I get this. And I can see here in this first part, I've taken the function and assigned it to x, f at x. Then I've solved f at x equals 4, and that's where I get my 2.3 from. Then I take that 2.3 and assign it to a. In this case, it turned out to be exactly 2.3, but it won't usually. So it's always better to take that number, whatever it is, and assign it to a constant. And then I just type in that formula exactly how I had it, and the calculator kicks me out an answer of 98.868, and that's the answer to my question. So I can now just go back over to the question, and I can write down my final answer and say this equals 98.868, and I'm finished. So the calculator makes this quite a lot simpler, and as you can see, the most important part, again, is getting the diagram right. Once we get the diagram, we've got a good chance of getting the rest of it. I hope that helps. Look at the next two videos if you're interested, and in those I'm going to solve part B and part C of this same question.